Welcome to this session. Would like to start because we have a very packed program. This is a session about a data model for open digital specimens and an emerging standard for minimum information about the digital specimen. And it also has some related lightning talks. We have a very packed agenda, as you can see. Although there's one presentation missing, one lightning talk from Minerva, so we will skip that one. We will probably have little to no time for questions. If we have, we will do questions at the end. If not, then I would like to ask you to go to our Google Doc, which you see here, this, the document about the session notes, and ask your question there, then maybe the presenters can answer your question later. Okay, so that's about the housekeeping. I want to go to the next slides. Okay. For those of you who has missed the presentation yesterday from Sam Leeflang, explaining some background about the data model and the relation to the new Darwin Core data package format, I would just like to give you a little background on this, so that you know how where it is coming from. A couple of years back, we had a consultation that was led by GBIF on digital extended specimens, which led to the common vision that we need to have a global network of digital extended specimens. And since then, we have started to work on the technical implementation of that, which led to the Open Digital Specimen data model, which you can see as a specimen-specific implementation of the Darwin Core unified model, the new model that was presented yesterday. So the vision is that you have the physical specimens that are managed in the institutions, and from these specimens you can create digital records with information, catalog information, and on top of that you can then extend these digital specimen records with extended information that is derived from the specimen or related to the specimen. So we need to have a data model that does not only capture the label information, the information that is in the catalogs, but also the extended information, the relationships with sequence data, chemical data, literature, etc. For the digital specimen, we capture the data in a fair digital object, and a fair digital object is an object that is consistent of three components. It has a permanent identifier, which is reusable. We use a DOI for that with extended capabilities, for instance, for versioning and for multiple redirects. It has machine readable metadata and machine actionable data. And that means that machines can also act upon the data and enrich that data with new information. A little bit about our roadmap. Currently, we have in Disco minted about 5.5 million DOIs for digital specimens and their related digital media, mainly images. And we want to go to 20 million DOIs by the end of the year, and further ramp that up in the next few years. We started an enrollment procedure for that because we want we aim to mint DOIs for all the specimens in the world. So if you have a Darwin Core dataset or an ABCD dataset available and you want to make use of these DOIs, then you can apply for that already. And you can fill in this enrollment form. That gets you on the waiting list because it will take a few years to mint all these DOIs. but the earlier you do that, the higher you get on the waiting list. We don't know yet if we have also capacity to create digital specimens for all the specimens in the world. We are currently focusing on Europe, but we would at least see if you are interested in that. Yeah, the minimum that we want to do is create this digital specimen identifier in the form of DOIs for all the specimens in the world. And that means that you can reliable refer to these specimens in literature, and also it allows you to better monitor the usage of these specimens in research. Okay. We can now go to the first presentation, which is from Sam Leeflang. Unfortunately, he could not be here today, so we have a recorded presentation from him.
Hello everyone, I'm Sam Leeflang and I'm one of the developers of the Disco core infrastructure. And today I will entertain you a bit with our openDS data model. We'll get to a general exploration of why we need this openDS, why we need this data model, and go through a couple examples of how we implemented it. So Disco. Disco stands for the Distributed System for Scientific Collections, and our aim is to accelerate the digitization of Europe's natural history collections. These natural history collections are vital for a wide range of information, from tracking biodiversity loss to informing policies and finding cures. And digitization is essential to increase the access of this information. And that might sound simple, but actually we have now only digitized about 10% of our collections. 90% is still only physically available. There's no digital record of it at all. That means that for 90% of the information, you would have to actually physically go to those institutions. And then still from the 10% that we have, it's often just a minimal set of information. It will be one of the other sessions in today where we'll go into MIDs, but often it's only a bare minimum that has been digitized. We think, and our aim is that through better collaboration and the removal of institutional barriers, we can accelerate the digitization and then the enhancement and creation of this data as well. So for that, we need some kind of infrastructure to start working on this data together collectively. And there we start here on the left side where you see the data providers. Data providers are often the institutions themselves which host collections, the natural history collections, have their own collection management system. And they expose it to Disco through either an ABCD, EFG endpoint, BioCase endpoint, or through a donor core archive. We harvest the information within Disco. We then harmonize it to the open digital specimen, and we'll make sure it will get a digital object identifier, DOI, and we create provenance records. So we change what at what moment. And our most important part is that we provide this interfacing layer on top of which anybody can now start building their own services. And we split those in two categories: the human annotation services, where humans can now start annotating these digital specimens. So I can start georeferencing them through some kind of website, or we'll create connections to citizen science platforms. So we get a broader range of humans involved than just the collection managers. And on the other side, the machine annotation services, where we try to leverage machines as much as possible to do the bulk of the work. Think about label transcription or creating connections to other infrastructures. In the end, we don't want to keep all this information bottled inside Disco. We want to push it to data consumers, which can of course be scientists and researchers, but can also be data aggregators such as GBIF. So this is kind of the landscape that we're trying to build, and to make this whole Disco ecosystem work and make it available for others to build these machine annotation services or human annotation services. we need this kind of common language that we have. So to create generic tools will require this universal common language over those tools. And for this is where we leverage the Open Digital Specimen. We structure the Open Digital Specimen as a document. That means that the whole specimen, all the information will be held inside a single object. We don't split it out, we don't normalize it, we keep it denormalized, and we base it on JavaScript object notation, JSON, with the addition of the linked data principles, where we add that context layer about what each term means and where it comes from. We'll base that on the fair digital object approaches. FAIR standing for Findable, Accessible, Interoperable, and Reusable, because we've packaged it now and we create these digital object identifiers. You can now find it either through our infrastructure or other infrastructure or any other infrastructures will be accessible to those as well. And because we've packaged this all with the additional context of the terms through the linked data principles, you can now start using it and reusing it in your own infrastructures or your own research project. In total, openDS contains about 8 top-level objects and has 30 classes with literally hundreds of terms. And most of these terms we reuse from existing vocabulary or ontologies. So, of course, Dharma core, we used those extensively, as well as audiovisual core, but we also use parts where we use schema.org for describing agents, or the provenance ontology for describing a provenance. So we're a bit broader in that sense. In this session, I will focus on the digital specimen, which is one of those top-level objects. A couple others are more focused at provenance, which is its own object with its own schemas, or annotations, which has its own schemas. And for the digital specimen itself, it's important to know that we base our work here on the Darwin Core conceptual model. We didn't try to reinvent the wheel. There are good people working on this, John Wiskowitz and Tim Robertson. And we're actually at a point where we're starting to see openDS as an implementation, a specimen-specific implementation of the Darwin Core conceptual model. I did a session on this yesterday if you want more information. Okay, let's start with a simple biodiversity specimen. How would we structure it? This is one of the butterflies from the Naturalis Lepidoptera collection, and we start with the digital specimen. So the digital specimen contains the top-level information. Think about on which collection it sits, on which institution, what the license of the metadata is, but also the version, which is the version of this object. So each change in the object information will generate a new version. We're keeping all the old versions, so this indicates which version you're actually looking at. It's important to note here that each digital specimen will have its physical counterpart at some point. So there should always have been something physical. Of course, it could get lost, or maybe it's been misplaced, but at some point in time there was this physical counterpart. And this physical counterpart would have a registration number. So that's important for us as well, that registration number. Of course, there could be other identifiers, and that's why we have this identifier class, where we can put additional identifiers for this specific object into. And this object has been collected at a certain moment in time, probably a collecting event, but we do have the opportunity to add multiple events to the digital specimen. We see a use case in it for living collections where there might be a collecting event, but also a moment of death and maybe an accession event. So we'll still need to figure this out a little bit, but there is an option to have multiple events. And then these events have a location and a georeference. The next part, of course, what species is that? And that's where we see I have an object identification and then an identification type, which is the taxon identification. And here we have room for additional extensions. So we also think we might get a chemical identification, because this guy's focus is a bit broader than just a biodiversity specimen. We're also looking at the geodiversity, which might require different types of identifications. Assertions, what's the length of the wingspan of this butterfly? And entity relationships, which I will go into more depth in a couple slides. And all of these, most of these also have relationships to an agent object, which is its own object. Think about assertions or collection. The collector is an agent, and that agent then has identifiers, and this is how we get these huge relations between all these different classes. So for a geodiversity specimen, I have here one specimen from the Royal Scottish Museum, and this is actually a quartz with multiple minerals on top of it. But those minerals didn't get their own registration number. Only the specimen itself got one registration number. So of course, for that specimen, we can describe the same things. But in this case, we'll have something called specimen part, through which you can describe specific parts of the specimen. So these didn't get their own registration number, but they're still distinct parts of that specimen that you would like to describe and give an identification, in this case, a holotype identification for both of these specimen parts. So that option is in there. And yeah, think, for example, for a rock with multiple fossils on it, if that only got one registration number, this is still a way to structure that information. Anti-relationships. So I think it's important here to stress that DISCO will only be a repository for specimen metadata and the associated images. We don't want to store information about sequences or about people. There are good repositories for those. So as a specimen, we want to kind of create this graph, this biodiversity knowledge graph published here by Roger Page, where DISCO will take care of the specimen, and we will then create links to other infrastructures, be it ENA for the sequences, or BOLT for barcodes. We'll have relationships to taxonomic data sources, Catalog of Life, to say, well, for this specimen is this species. If you want more information about this species, go to this place. For people, we'll probably have Wikidata. We'll also have support ORCID. So actually, for each change being made to the specimen, we'll say who created that change and then point to their ORCID. That's a vital part of our infrastructure. And with the ORCID, you can find more information about who that person actually is. So we don't want to get all that information in the system. No, we want to link to all these different sources. That's why we use the entity relationship object. And through all these linkages, we're building this kind of digital extended specimen. It's not just the specimen metadata. It's this whole range, whole network of relationships to all these other data sources. Okay, then last part, documentation. So we described all our data models as JavaScript object notation schemas. So these are schemas for how the JSON should look like, and we put them in GitHub, which is our single point of truth. This is where we can discuss and request changes on those, and we then automatically expose these to schemas.disco.tech, the web page, really technical, where you can find all the schemas. And all our code and other documentation is based on these schemas. So we ourselves are using these endpoints to generate the code that we use in our code base. And anybody can start using these endpoints, these schemas, and say generate objects in my programming language based on the schemas that have been published. This is also where we generate our documentation pages, terms.disco.tech, and our OpenAPI or API documentation. And we have already had others using these schemas to generate their code as well. And if they do, we know for certain that we're interoperable and don't run into any issues. So that's our single point of truth. For the data models themselves, I recently created the first set of triple SOM mappings for mappings for openDS and Darwin Core Archive, or openDS and the ABCD EFG. It's still a bit new to me, so they are available online. You can have a look at those. And please feel free to comment, because it won't be perfect yet, but we're trying to document how we do the mappings. And the same counts for how we expose it through the Dharma core data packages. The triple SOM mapping is available as well there. And that's where I want to conclude talk. So I hope that I've shown that openDS provides us with this extensive and extensible framework. We know that we need to make improvements. I'm really looking forward to the publication of the mineralogy extension on the work that has been going on there, so that we can better include all the information from the biodiversity specimen. OpenDS is fair, compliant, and fully interoperable with the Dharma core data package, as we're using the same Dharma core conceptual model as our basis. And in the next session, Sharif Islam will show a bit more about the next step we want to make regarding controlled vocabularies and how we want to leverage those. And I would like to thank you for your presentation. And any questions, you can reach out to me with any questions. And Wouter Addink is in the audience. He can answer your questions as well. Thank you.
Okay, we quickly go to the next presentation from Sharif Islam, which is also a recorded presentation.
Hello, I'm talking about fair terms and vocabs for digital specimen. In this talk, I'll talk about fair implementation and how it fits into the discourse design, and what's our current plan on this. Just a reminder, when we talk about FAIR, we're talking about findability, accessibility, interoperability, and reusability. These ideas are in the context of how machines can use and understand different aspects of data and other digital objects. So the challenge we're dealing with is that different research domains often describe and use the same fundamental concepts in different ways. Although these concepts belong to a relatively small set of classes, but the challenge is when we use them in a data set, we see fragmentation, linking issues, and also machines cannot interpret these things very easily. So we know that it matters how we link, map, and reuse different properties and concepts. FAIR principles provide some guidelines for machine-readable and machine-actionable components, and these are not just for the data, applies to the concepts and the terms and the properties as well. And the goal here is that we want to reach some sort of consistency across infrastructures and data sets. Again, this does not mean that everybody has to use the same system or same terms, but there has to be some alignment between different systems. So as you notice, I already introduced a few things, terms, vocabs, concepts, properties. So what do we mean here? So in a formal sense, vocabulary defines the terms, and the term may be a property, class, or a controlled value. We also have a formal ontology that describes the relationships, and then we have some constraints on these properties, what values could be used. And I borrowed some of these ideas from the community, specifically how it was described in the Tadwick vocab maintenance and specification task group. Within the context of DISCO, we will be primarily interested in the terms and the control value, and I'll show an example in a minute on this. Some of these ideas also came from semantic web world and the idea of simple knowledge organization system, where they talk about concept, classes, and the relationships between them. And you will see these ideas also coming in within our discussions. So why FAIR terms and vocabs matter here? This is a guide that came out a few years ago where you can see they're providing guidance how to make vocabularies fair, providing PID, metadata, licensing information, and things like that. We'll be also using these guides for our design. Let me give an example from Darwin Core to understand this better. So let's say we're interested in the life stage, and we know that when we're collecting data, this information is there, and it occurs within the Darwin Core occurrence dataset. So in this example, the life stage is the term, and of course, this is a property in the data schema. And then imagine in this implementation, we only allow 3 values. An adult is one of the control value that's attached to the life stage. And of course, it has relationship to the occurrence dataset. So together, all these belong to the Darwin Core vocabulary, but we have the term and the value that's related to the term. So how this fits into the DISCO ecosystem is that we have the digital specimen, which is our way of identifying and describing the digital specimen. And then they have, within these specimens data schema, we have different properties, semantics, and attributes, and that's where the FAIR vocab and terms will come in. We will have a dedicated namespace, ODS for Open Digital Specimen. The terms will be managed as FAIR digital objects. That means that each term will get a PID. In metadata and machine-readable serialization, we'll describe the relationships to the other terms, and of course, there will be some constraint on the values to ensure consistency. Example from openDS. So let's say we have a term called topic discipline that will have a PID and metadata. And then let's say there's only 4 allowed values. So these are our control values, again, with their own PID and metadata. This is a proposed data schema we're working with. Here you can see the ID and some other metadata, versioning, and some provenance information. And then at the end, you'll see there's a list of PIDs of the values that's linked to this term. And again, each value also has a PID and treated as an FDO. So the benefit of this is that we're treating them as FAIR digital objects. That means that they're linkable, reusable, and it's a path towards full FAIR implementation. We have a clear separation of terms, properties, and values. Even though we are creating new service and introducing some new terms, these are giving us some flexibility and governance, but we're maximizing as much as possible existing standards and other vocabs. So if there's something from Darwin Core GBIF or Category of Life we can borrow, we will use it, not create a new term. You can see our current implementation in terms.disco.tech, and we'll have a full FDO implementation coming in 2026. Thank you again for your attention, and I would like to thank my colleagues and also various community members that provided feedback to this idea. Thank you.
Okay, the next presentation is from Elspeth.
I'm going to drop something. Apologies. 1 second. Yes, sorry. Apologies for that. Yeah, so it's really great to be here to tell you some of the information about updates that we've been making to the minimal information about a digital specimen, MIDS. So first of all, I'm just going to check. Get my glasses off so I can see you. Can I show of hands of people who have not heard of MIDS before? Okay, thank you very much. It just helps me to make sure I give you the information that you need as well. Great. So where are we? First of all, what is MIDS? And for those people who have not heard of it before, I can tell you a little bit about the background of it. First of all, it's a measure of completeness of a digital specimen. So as we're digitizing our collections, we want to be able to measure that progress of digitization. And so that's what MIDS is designed for primarily. It's got different levels, which we'll go into. I'll show you some of those. And starting from like MIDS level 0, which came in as kind of pre-digitization level, which is pretty much records the specimen's existence, but not much more than that. Tells you that it exists and where it is. But right up to MIDS level 3, which is where we're getting into the territory of the open digital specimen. That's the one that's about linking to data and allowing those links to be made. What MIDS is not is it's not a measure of quality. That became apparent in the development of MIDS, that is too difficult an area for MIDS to manage. It's more about the completeness and data richness rather than quality. So as we all know, the digitization of the world's natural science collections is expanding massively. However, digitization, yes, apologies for that. Digitization in scale can really only be done in stages. And that's what we're seeing with all the massive digitization programs. So when I last looked, there were about 265 million preserved specimen records in GBIF. And I mean, that was just a short time ago. So that will have gone up a lot since then. But that means that we have a need to provide a way of measuring the variation in the level of digitization in all these specimens. So what I want to talk about here is the work that we've been doing with MIDS. And in order to talk through where we are with it, I also want to talk through the launch of the new MIDS website. Now, I'm going to emphasize a lot of times during this talk that this is a draft. We're not yet complete, but this is an opportunity. It's a really nice place to go to get a better understanding of MIDS, and a really big shout out to Ben Norton, who's done so much work on its construction. So I'm not going to have time in this talk to go into huge detail in any of the parts of MIDS, but really I hope you can explore the website, possibly as I'm talking, but also later to dig into more detail in there. So to give a quick run through of the website, and I can talk about the MIDS structure at the same time. The information elements page is one of the key areas of the website, and it contains most of the normative information that will be the standard. We'll obviously make that clear what is normative and non-normative, so that means that we'll talk a little bit more about that later and what normative will mean for MIDS. So first of all, this is where you're going to find the information about the MIDS levels, and each level is defined. And really importantly, we're bringing in the purpose of each level so that that becomes clear for people. And you'll find that the purpose is really always a key part of the website for MIDS. So to achieve each MIDS level, selected data must be present in the specimen record. So for MIDS level 0, the record must include the organization in which the specimen is held, as well as a specimen identifier. The MIDS levels are cumulative. So to achieve MIDS level 1, you must already have achieved MIDS level 0, but in addition, you're going to need information about the license, the modified date, the name, and the object type of the specimen. And so on for as we go up the MIDS levels. So the information that are recorded for each specimen are categorized into information elements. Now, these are not terms. They're related to terms, as we'll see, but they're not terms in themselves. So we've using the word or the words information elements for them. And in this page, you'll find a structured listing of all the current information elements. So that includes a definition, usage notes, again, purpose, and examples to hopefully help people understand what the information elements are. The MIDS levels and the information elements, though, are only part of the picture. For MIDS to work, they need to be connected to the specimen data structure. And this is done using the mapping. And again, we're using the SSOM mapping, the simple standard for sharing ontology mappings for MIDS. So the mapping structure is proposed to be normative, but the mapping itself is planned to be non-normative. And that means that MIDS will be able to develop in line with changes in Darwin Core, ABCD, and other standards without actually requiring the ratification of these updates. So it's going to be, it'll make MIDS a little bit more agile for maintenance. So for each information element for biology at the moment is currently mapped to Darwin Core and ABCD. And work is ongoing to undertake a similar mapping process for geology and paleo terms and make them available. So we decided at quite an early stage at higher levels of MIDS, it was necessary that the information that were being captured were too diverse for different disciplines. So we created different kind of pathways, if you like, for MIDS for each of these disciplines. Sorry, for the information element and the term mapping. And then there's a resources section. And in here, you're going to find links to tools that have been developed for the calculation of MIDS levels of our data sets. And the one thing that we would want to make clear, MIDS is not yet ratified, as I said earlier, this is draft. So there have been some changes which are not necessarily reflected in all the tools available. The one that we're really keen to direct people to at the moment is the MIDS calculator, and that was developed by Matthias Dillon and Lynn Delgat at the Mesa Botanic Garden. And that's been recently updated to enable the calculation of Darwin Core archive datasets, as well as ABCD datasets for biological data. And I'd really encourage anyone who's interested in finding out about the digitization status of their collections or anyone else's collections to try this out. It's super easy to use, and especially with datasets downloaded from GBIF. And finally, there's a glossary to help with some of the key terms used in MIDS. And there's some background information in the About page as well. So this is your chance to try it out and explore your data sets. It's a really good way to get to know your data sets. You might be surprised at what you see. Use the tools available to calculate the MIDS scores and dig into the results. It's very easy. We've seen several times when we're working with people and myself to look at our data sets. We're finding that although we're capturing data, we're not necessarily making the data available on GBIF, or it's not mapped correctly when we're uploading to GBIF, so they're not accessible to others. So some of that data is really easy to actually make available. And you can, by doing that, you can achieve a higher MIDS level for your data. And make it a better resource for users. So we're currently in the ratification process. We've got a super team of expert reviewers who have started digging into MIDS, and we're hoping to go to public review stage early next year. So keep a lookout for information about how you can participate in that. And finally, I really want to thank all the members of the TADWIG MIDS task group for all the work that they've put into building what we've got at the moment. And yeah, thank you very much.
Okay, thank you, Elsbeth. Next presentation is again a recorded presentation from Matthias Dillen.
I'm Matthias Dillen from Reusable on the Garden, and today I'm going to talk to you about MIDS. In particular, I'm going to talk to you about projects that we've been working on in this task group over the last couple of months, integrating MIDS in practice and at scale. With this MIDS, you may have seen Elizabeth Weston's presentation right before mine, where she goes into much more detail. But in short, MIDS is a new and upcoming standard in TADWIG, and it's a set of different information elements, that is, properties of specimens that are important to be digitized. And we have distributed among incremental levels of digitization, going from 0 to 3 plus an extra category for undigitized. These elements are mapped to data standards like the OpenCore using the SRM framework, a simple standard for mapping standards to one another. These mappings consist of a tab-separated file, the mappings themselves, essentially a table, and a YAML file with metadata for the mapping set, including its version. You can see the mappings and find more info and documentation on the next website and following these links with the QR codes. The mappings take part of the calculation process, which results ultimately in this level scores per specimen records from 0 to 3 or -1, and a binary value for each information element, whether it was met or not, whether it's present or not. This is what one of these mapping tables looks like. I'm not going to go into much detail. It essentially maps the information elements to, for instance, in this case, dollar code terms. And we've used those to calculate MIDS levels for all the specimens in GBIF to see how that works out in practice and what sort of results we get when we do that with the correct mappings that we're using. So we took a snapshot of GBIF using the SQL API mapping view, resulting in around 265 million preserved specimen records. So that's occurrence records with base of record equal to preserved specimen. This results in quite a big data file, but the calculation itself was rather efficient and can be run on one single laptop if it has at least more than 16 gigs of RAM. And it took about 2 hours, but there's still lots of room for improved efficiency in this matter. To do this calculation, we reused the code from the MIDS calculator tool, an RShiny app developed earlier for doing MIDS calculations, but we scaled it up, enabling to run the code in batches of 10 million and without the overhead of the RShiny interface, just using the command line to run the code. As an output, we get indeed lots of DSV files containing the binary maps, the 0 and 1s for the MIDS information elements, and a MIDS level score for each of those 265 million specimens. So this is what one of those simple maps looks like. There's lots and lots and lots of 0s and 1s and a few 0 to 2 values. When you add these on a graph, so this results show the different specimens aggregated across different information elements, whether they are met or not. Blue is met, red is not. And going from left to right, it lists all different information elements, starting at the ones only required for the limits levels, 0 to 3 on the right. You can see much more net on the right, because that's where, of course, the more strict and categories arise, often identifiers for different specimen properties. And you can see at the overall MIDS level scores, shown on the left, that most specimens were stuck at 0 with only very select using these two. Reaching MIDS level 3 with this setup, as you can see, was impossible because the media ID, almost completely on the right, was not possible to be mapped through the SQL API and is not the often that used in GBIF anyway. The results of this, we can see what the most impactful MIDS elements are. They're listed on this slide. I don't have time to go into detail for all of them, but I'm going to highlight a few very important ones, in particular organization, object type, and collecting number. The organization is defined in MIDS as a term to indicate in which institution the specimen is held, is a very key property because it is a derived phrase which meets level 0, meaning that if you don't achieve this property, if you don't map it properly, you will be stuck at this level -1, and your specimens will be undigitized. This is the case for about 10 million specimens in GBIF at the time of the calculation. So these specimens do not have enough organization, making it, in principle, impossible to resolve those digital records to the physical specimens wherever they reside in the world. That's the diamond, for which you can see the DNA on the slide. You see that almost half of these are from an iron SDC dataset, which contains essentially sequence data. The purpose is the voucher specimens associated with those sequence data. And indeed, quite a lot of these voucher specimens do not properly or not even at all result back to the physical specimen, wherever that is in the world. And it's just unknown to which institution they belong. There's also other datasets with institution IDs at the record level. This could be a mismapping, but it could also happen with composite datasets, in particular when there's privately collected specimens in there, residing in private collections for which it's not straightforward to make an organization ID. Second, we get object type. This is a property that has been subject to quite a lot of discussion in technical circles the last couple of years. We define it as a general term to describe the kind of specimen. So, varium sheet, pinwheel insect, microscopic slide, stuffed animal. As we see, more than half of the specimens in GBIF currently do not map this property as we specified in the mappings, which is currently all the maps to the varium co-preparations term. The causes for this are that oftentimes people bury their data as one single block, so all the specimens are the same, and then the object type is implicit at the dataset level, for instance, replication for varium sheets. But that is, of course, not easy to infer into read-by machines when you do this calculation process. There's also the issue that in Darwin Core, currently, still mainly it's only preparations that can be used. Material entity type is a relatively new addition and is still not widely supported or at least used in the data publications, though it is a ratified term. As part of the Darwin Core data package process, there will also be a new class material category, which may also help in converting these data. People extend the mappings to these properties as well, but it currently is still a chicken and egg problem in terms of the miscalculation process. Finally, we get the most erratic of these three, collecting number, which is another to the specimen at the time it was recorded. This is just a string number that is attached to the specimen by the person who collected it, and it can be all sorts of different. All sorts of different forms, but it is very important when it is used because this is oftentimes used as an identifier for the specimen when referring to it in literature or in sequence databases. But it's not always used. Not all collectors use these kinds of numbers, so it is important to be digitized when it was used, but we don't really necessarily know at the time when that was, and this underpins the sort of the need for vocabulary to be able to specify that this property just is not available and applicable for these kind of specimens. And then we can also accept these kind of values during the miscalculation process. Because as you can see, again, this is more than half the specimens covered that suffer from this problem right now. So that was a going through it in short. I really don't have too much time to go into all the details. But what I wanted to say really with this work in this presentation is that assessing risk levels like this can relatively easily be done and redone. There's some issues with the version of the underlying data, but that is a bit of an external problem. And when you do this, these scores can really show various useful insights on the digitization status, which is what we were interested in, but also on the data modeling done by different data providers before they submit their data to an aggregator. And therefore also inform kind of development in terms of promoting interoperability. The mappings, of course, have a high impact on how this sort of work and how these results work in practice. But they're out for discussion. We will hopefully soon enter public review with the mid-standard, and they can be adjusted with different versions to compensate for instance, data validation methods with, as we suggested before, known unknown values, but also other particular data modeling issues that result in fixed values that should not be part of the, for instance, the miscalculation process. Just briefly, I wanted to thank all the people in this task group for all the very useful and fruitful discussions over the years. The Disco Fauna 2 project for funding me to do this kind of work, and I should be here online for any questions. Thank you.
Okay, the next speaker is Ben Norton. He also has a remote presentation. Yes, it seems to be that unfortunately we have only a presentation but not a recording. And Ben is not here today, so I assume you have to skip this presentation. That means that we go to the next presentation. We have now 3 lightning talks. And the first lightning talk is from Christina. Let me see. Christina Silveira Cerejo.
Hi, everyone. Good afternoon. So my talk is going to be quite short, but anyway, is about the contribution now to biodiversity data in the Global South, digitization progress in open data through the CBBR at Museu Nacional, where I work. So I'm Cristiano Cerejo, who's the team that work mainly in this project. So Museu Nacional houses one of the largest natural history collections in Brazil, South America. And Brazil is a diverse, very diverse, country with nearly 20% of world biodiversity. And the Museu Nacional is the oldest institution, scientific institution in Brazil. It got 2 years old and has huge impact in fire in 2018. Okay, let me see here. So he's already, the area also recovered, and he is impact inside the building. So what was mainly actually modified was the main building, and I'm going to show you that things will impact, but that was huge. Okay, let's go. Okay, this is not an overall collections. We got 26 natural history collections, aside of the cultural ones, which is not here, and with 36 databases across 5 departments. And the fire impact was nearly 80%, especially because of the entomology, group. So is the botany, entomology, vertebrates, geology, invertebrates. So entomology nearly all is gone, nearly. And we got a strong impact also in arachnology and malacology. Yeah, these were inside the palace and was huge impact. But we got some rescue, some 5 1,000 items was rescued, and catalog items after the fire is the yellow bit here. So we continue on after the fire, of course, moving on. Okay, come on. No, sorry. Sorry about that. Okay, so the objectives of this project was to digitize the collections, especially the biology collections, especially type material and historical, and other types of specimens that was important. Standardization protocols and workflow of the metadata through specify and Jabot. So for the zoology, we are using specify, and for the botany, we already are using Jabot, and collecting data available through open platform exceptions through web portal. That's going to be through the specify, and CBBR and GBIF. CBBR is a node of GBIF and OBIS. So interesting, these photos here are already the new facilities for the collections that were destroyed. And we got a new area of 40,000 kilometers with this new units. So we are now much in a better situation, so we can invest in this digitization project. Okay. So the CBBR, which is the System of Information Biodiversity in Brazil, started in 2015, and we started to digitize and to put the data with Darwin Core inside the CBBR, although with few images. So the main point here is to increase the number of images. Nowadays, National got 43 databases with nearly 500,000 registers in CBBR, and digitization of entomology and malacology collections was crucial for info recovery after the fire, because they were having previous digitized before the fire, so it was very important. So these images here are before the fire, as well as these ones here. So, but these are not CBBR yet, so doing now is to efforts to do some treatment in the images and to put in the CBBR, which is going to be available later on in GBIF and the whole population. By 2022, we got some financial support from FAPERJ, and we started the CoDigi project. And together with that, we raised the lab, the CoDigi lab. So here we got the camera, the professional camera, with the programs, and also equipment to take smaller animals, so we can take photos from larger animals and smaller animals. We got people, financial scholarships, and also people from the museum who's from the staff to work in this lab. So here are some of the photos that was coming from this project, especially as an example. So I'm not had time to go through all. So here's some images of the invertebrates, collections. You got 14. That's the number of registers, and type material, nearly 7,000 registers, and highly representative of marine fauna and forest opinions we got now. And these are all type materials, all types and parts. um, um, put it in the computer to be, connected with the data inside specified, and then we can then put it out in a proper way. Here's another example, okay, of the vertebrate collections. So this is also type material, especially, really, antique historical specimen. And these were photographed, so we edited in this project too. We did all the primates and vertebrates from the mammals in this project, and nearly 400 registered. The vertebrates were not affected in fire, around 10,000 type material, and valuable historic and rainforest specimens. So just to conclude, this is a little bit of the what we raised since 2022. So here is the total specimens and species. So nearly 5,000. That's the numbers, and these are the whole groups that we are working with. Botanic with the body is much easier as a 2D, and we have actually much more digitized. This is just this, information from this project, and the type material, we got these 3,800 species from all these groups already, done, and we are editing what was done in the past in CBBR. These images that was, not treated, so we're treating these images that we had before to attach inside, the database and put it out in some way. So, yeah, it's many groups. We needed to have the specialists, the curators with us, and we are going, slowly. Got this lab that is multi-user, so the whole museum can go and use this lab, and most of being, showed here is coming out in a special volume of the Bulletin of Human Society as the Global South Biodiversity volume that we are actually put this data together to show that Museum survived this huge, fire, and we are continuing on to put this data off. That's it. Thank you. That's the team that is involved. We do some also extension programs to show the importance of digitization, and that's it. Thank you.
Thank you, Christina. The next presentation is from Juan Manuel Daza.
Can I take this out? Okay, I think it's better for me to do that. Okay, so good afternoon to everyone here. So today I'm going to talk about maybe one topic that it should be presented 40 years ago when all these standards started, but hopefully it's not too late to talk about that today. So let me see. Oops. Este. Okay, so obviously everyone in this room is familiar with this flow. So we have specimen, we have data, and we also have repositories where we put that information. And like along all this time here in this conference, we've been talking about all these standards that has been applied and new things that have been improved to digitize the specimens. However, in research, there's sometimes that other data has been gathered that is a structure, and that needs to be seen carefully. So if we can actually put them in the same systems that we were talking to. And for this, I'm going to talk about this time about this group that is called anomalies, but I think that probably many of you that have been working in other groups maybe will find some similarities what I'm going to talk today. And I use this group as a model because in terms of is the genus that has actually is the animal that has the largest species diversity. And so it's very significant that it's very, very well GBIF. So we might think that this is a model for all the data that has been generated in this group, but that is not. To show that, I'm going to address two main questions with this group. That the first is there is a standard in morphometric trace nomenclature in lizard anoles, and the other is how morphometric data is integrated with the first principles. So to do this, we look at all the papers that we could find that are actually is here that actually is including morphometric. And the first thing that we started was dividing in different topics. Okay, so how morphometric data is used in different fields in annual research. And not surprisingly, the field that is most used is systematic. But as you can see also in ecology and evolution is being used morphometric data in this group. The other thing that we actually, holy moly. So I lost the really? Could you put it in as a PDF or because you can see it the points, right?
Lo mismo que está haciendo acá. En la siguiente. Dale la siguiente. No, entonces no.
Okay, so I'm sorry I didn't. Maybe I should send that as a PDF. But what I want to show here is that there is a wide variation. Maybe it's enforced in the next slide, but there's a lot of variation across the study. There was like dots in here showing there was like a range of points representing each study that actually shows how variable are different studies using different morphometric variables, which means like not all the publications, neither evolution or systematic using the same morphometric context. But most strikingly is when we look at the how they actually define those morphometric variables in the papers, we found also a high variation in studies. Actually, they don't include the names or explanations for the concept. They just only say, okay, well, we use 30 morphometric variables. And at the end, they show the analysis and figures, but they never actually explicitly mention. And so we can see it here as a summary. Here in the x-axis, we see all the morphometric because we unify like more than 70 morphometric variables. And here, different studies, and you can see like not every single study are using the same morphometric variable. Neither they are kind of combining or sharing the same variable in different levels. And to make these things work, not of them, just very few are like raw available in repositories. And now that we have this economy in North, like the global south, global north, but just to mention that the data in the global genus is from the neotropics. It's pretty much all the specimens are in the global south. So with that, just I don't bring positive conclusions, but I just wanted to bring maybe an attention that we have these, and I change this name for the group that you're working on. Similar. So we have transparent. We have actually to have, there is a paper, recently paper talking about terminology. but because the egos of researchers, they don't want to use whatever another person is proposing. So I think that is to kind of have this attention and say, okay, maybe a committee, maybe the TDY can actually move forward in this very important group as a model system in biology. And with that, for everyone.
Thank you, Juan. The next lightning talk is from Olive Adams.
Yeah. Oh, hi, I'm Olive. I work in the digitization team at Kew Gardens. And yeah, today I'll be talking about quality assurance in large-scale herbarium transcription. So Kew holds one of the world's largest botanical collections with 6.4 million herbarium and 1.1 million Hungarian specimens. And in order to increase access to scientific data, Kew has run a 4-year digitization project with the aim to produce both high-resolution images and accurate transcriptions. Whilst a contractor digitized all of the standard herbarium sheets, we also had our in-house team who handled the bulkier and more complex material. And today I'll just be focusing on the QA of the in-house transcriptions. So we followed MIDS Level 2 standard, which requires a catalogue number, a digital image, and structured metadata. And we found that this level balanced both time and cost with our project goals, while still providing enough information for the data to be findable and useful in GBIF. So balancing that rapid processing of large volumes of material with the need for accurate data can be challenging. So in order to tackle this, we built a comprehensive QA workflow. So how much do we check? We found that to balance feedback with workload for 27 digitization officers, it worked best to QA 25% of new staff records, and then this actually reduced down to 5% once they were more established. How do we check? So QAs will use barcode lists to open records in our integrated collections management system, which is called Earthgate. They'll then compare these records with the relevant image and then log their sessions in a tracker to avoid any duplication and monitor our progress. What do we check for? So we look at key fields like barcode number, storage and legal information, collector and locality details, and then also the most recent identification. How do we give feedback? So any minor errors, such as spelling mistakes, are just corrected directly by QA. And then any major errors, such as missing storage information, are fed back to staff to fix via bi-weekly emails. And these emails also include any positive feedback. And we actually learned that providing that timely and constructive feedback should take priority over clearing any of your QA backlogs, not only because it prevents repeat mistakes in the long run, but it also supports staff confidence. And then, yeah, finally, how do we reduce errors long term? So we've developed supporting documents, such as kind of common collector signatures. We also use Teams channels and chats to share examples of difficult handwriting. We also have a team of curated botanists to advise on any exceptional sheets. And then we also have the data managers who run their own kind of automated checks to bulk clean our records. And all of this kind of ensures we have consistency and accuracy across our data. So yeah, thanks for listening. And if you want to know any more, feel free to come find me afterwards.
Thank you, Olive. Now I have some good news and some bad news. The good news is that we have been able to get the missing recordings, so we can proceed with the presentation from Minerva Singh and the presentation from Ben Norton. But it will also mean that we go a little bit over time. I think it's worth listening though. But yeah, you will get a little bit later for the coffee, unfortunately.
Hello, I'm going to talk about information extraction from historical cards using AI, because this is the work I've been doing at Natural History Museum under the supervision of Dr. Ben Hartley and Ariana. And my work involves using NLPs and large language models to extract information from handwritten cards. The aim of the project is to extract structured data from scanned images of species records, handwritten texts, and organize them into a tabular format for easy analysis. So these are the handwritten records and cards we have. So it's quite a diverse lot. This was for bird skins, a tag, a proper written card, cards in different formats, cards with crossing outs on them, and so forth. So it's really quite a broad church in terms of the historical species data. As a part of the museum specimen card data extraction pipeline, I transformed these historical museum specimen cards into structured digital data through automated image processing and intelligent text extraction. The system begins by pre-processing digital card images using advanced OCR techniques and then leveraged GPT-4's natural language to accurately extract and categorize key species information, which you can actually see here. So this was an example data extraction prompt. We specify all the different labels on the cards and actually guide the prompt into doing what it needs to extract. And then these were the kind of data and information I received, including species name, locality, collector, and so forth. And these were the initial LLM outputs. And then the next part of my project focused on correcting the LLM extracted species names using RAGs. So RAGs stand for Retrieved Augmented Generation. A user prompt triggers data retrieval from large external sources, example GBIF, and the retrieved context is passed to a generator to produce an informed response. So this was the LLM prompt for RAG-based species name correction, and the prompt actually urges the model to be a biodiversity taxonomy assistant, take the external information, example from GBIF or eBird, and then correct what the LLM extracted from the card. So we managed to, the RAG output, it identified the top and potential candidates. So the original species was identified from the LLM. The top candidates is what RAG produced for us, and then comparing the LLM record and the top candidates, the top species was identified. And if ambiguity still persists, we have the option of consulting experts with the top candidates. And then some of the other work that I've done involves detecting crossed out entries on cards. So you already saw that some cards are crossed out. So, and these need to be detected. So this was a detailed prompt to identify crossings out in the different parts of the cards, specify the different parts, and the prompt sought to identify if it's been crossed out or not. Now, the end goal of our research is to develop a universal workflow for identifying different card types and extracting information. So a unified workflow emphasizes using generalized Claude or OpenAI prompts to automatically identify the different cards, whether it's an egg card or a mammal card or a skin card, and then extract their information automatically. Thank you.
And we can go on with the next presentation from Ben Norton.
Hello, my name is Ben Norton, and I'm going to present on the compound specimen model. And I want to thank you all for attending the symposium and this conference and for attending this recorded session. So let's get started. So a quick outline. Today, talk about conceptual models in general, the simple and the compound model, what they are, how they're similar, how they're different, an overview of the compound model, a couple examples that illustrate various facets of the compound model, and then talk about the solutions and opportunities that the compound specimen model presents. So first, what is a metadata model? It has shared vernacular, it has a shared understanding. So we need to start on the right foot. So to put simply, a conceptual model, a metadata model, used interchangeably, it's not a database schema. It's not an implementation plan or a user interface design or application logic. It transforms implicit knowledge into explicit shared understanding that serves as a validated foundation for all subsequent technical design and implementation work. It is the foundation of the house. It is what things are built upon. It is how you can build a standard upon it. You can build and in fact, the mineralogy extension, a new extension Darwin Core coming out, is based on this model. You can build a collection management system upon it. Anything you want to. It's that foundation. And it governs how information about object is described, organized, and made accessible. All right. So first, the simple specimen model. Simple specimen model, to put simply, is a single determination of a single physical object, that it's cataloged object, that has a catalog number. One and only one determination. The overwhelming majority of biological collections are based on a simple model. Most of the specimens are simple specimens. And then as such, most collection management systems are based on the simple specimen model, one determination for one object. Here are a couple examples of the simple specimens. We're all very accustomed to these things. In this particular, these are all specimens from the National Museum of Natural History, the Smithsonian Institution. You have a bird, fish, and a shell. These are invertebrate zoology, ichthyology, aves collection objects. And in this simple specimen, you have the simple object, you have a locality record, you have a collecting event. These are single records, single place, single time. Preparations, you may have multiple preparations, but they're all associated with that centralized object. Same thing for determinations. You might have multiple taxonomic classifications. These things do change over time, right? But all of them are still connected to the same entity. They're identifying that same individual object. So the question is, what happens when it doesn't work? What happens when you have multiple things that are physically attached into one cataloged object? Well, that's where the compound specimen model comes in. Compound specimen model it's a digital representation of physical specimens where each specimen record is divided into one-to-many constituent parts, each identified by a mutually exclusive determination. So it's multiple identifiable things in a singular cataloged object. And in here, on the left-hand side, you have the shared metadata about all parts. Same locality, same collecting event, preparations all connect to the object. Very straightforward. Where it starts to deviate is on the right side, when you have each part has its own determination and may have a separate geologic context. You might have a specimen that's at the KT boundary that has a formation on top, formation on the bottom, two formation, one object. So that in that case, you have two geologic contexts or in a single object. So to define these things, a compound specimen, well, it's a collection object comprised of one or more parts, unified by physical attachment, and that object's identity depends on the identity of its parts. What is a constituent part? Well, it's a physically discernible and proximal part of a compound specimen, identified by a single determination based on physical and chemical exclusivity relative to the parent object. And then each part has a part type, belongs to one and only one part type, and those are a high-level set of atomic domain-specific values for categorizing constituent parts, rock, mineral, ore, meteorite, these sort of high-level things. Each one belongs to one and only one. So to illustrate the compound model, I think it's best to work through a couple examples. So these are going to increase in complexity. The first two are very common to most collections. You'll probably find it in your own collection if you go to the museum you're affiliated with. I almost guarantee you're going to find the first two in the collection. The third one, not so much. It's a more complex example, which we'll get to. So first, stilbite and fluoroapophyllite from India. It's a very common specimens. On the left-hand side, now these are all stored in the simple model. So on the left-hand side, you have one name, one determination, and it's fluoroapophyllite. And then in the description, it's fluoroapophyllite's primary, stilbite associated. But if you look at the specimen, the fluoroapophyllite is the green, the stilbite is the white. It's roughly 50-50. This was a judgment call. And what had to happen is this specimen, the compound model wasn't available. And so the curator, collection manager had to pick one and only one. So they went with fluoroapophyllite. Although if you look at it, it's fairly equal proportional. And in that particular location, it's very popular for both fluoroapophyllite and stilbite. On the right-hand side, this is from the University of Arizona Mineral Museum, the opposite occurred. And this is quite common. In this one, they called, okay, that's stilbite, and it's stilbite with fluoroapophyllite, and the associated mineral is apophyllite. But there again, it looks roughly 50-50. And here the pink is the stilbite, and then the green, light green, is the fluoroapophyllite. So this is how it works, and you find this a lot, this sort of back and forth, because they were forced to pick one. It's highly subjective, equal proportions, but there was no mechanism that allowed you to identify them as siblings. Because really what this is one object on the left-hand side, an MNH 171329. That's the object. It has two parts, 50% apophyllite and 50% stilbite, and those are equal to one another. And the same thing for the right side. The next example is one of my favorites. It's an almandine schist from Fort Wrangell, Alaska. This one happens to be from the Yellow Peabody Museum, 053404. These are common in most collections. And in fact, if you'll do a quick search of these across collections, you'll find the name, a lot of different names. You'll find it as almandine, which is the one here. You'll find it as almandine and schist. You'll find it as almandine schist, and you'll find it as garnet schist. Lots of different names, and a lot of names are compound names. It's calcite and quartz. It's amethyst on calcite. It's garnet and schist. These types of things, because they're all forced into the simple model. And so you have to make these overgeneralizations that lose context and lose meaning by being forced into it, which is why the compound model is so critically important. So now this has also impacts for the Synod specimen network. That garnet's been dated. It's Sumerian neodymium dating, and it's dated to 92 million years. With the simple model, that radiometric dating record is connected directly to the object. No differentiation. Now, was it the almandine? Was it the biotite and the schist that was dated? It's unclear programmatically. Now, sure, you can look at the comments, you can go through this, but if you want to do things on scale, it needs to be machine accessible, right? And in here, that relationship is defined between the dating record and the entire object. And that's false, right? It's not the entire object that was dated. It's the garnet and the schist that was dated. And in fact, that age dating, the garnet, allows you to interpret the metamorphic event that resulted in the schist formation. This is really important. The simple model, you lose all that. With the compound model, you get all that. And so here, that radiometric dating record is connected directly to the almandine, because you have two parts. You have the schist and you have the almandine. You connect the radiometric dating to the almandine, which is where it should be, and then you can interpret the medium grade metamorphic event that resulted in the schist formation when that happened late Cretaceous. And so you can interpret these things. It's really nice. And this is one example of many. And so you can make interpretations. It provides the proper context. And really, without it, the extended specimen network is not possible. Imagine if you had a DNA extraction and you didn't know what part, let's say you had two birds in a box. You didn't know which bird it came from, and you're not sure where in the bird tissue was extracted. It came from anywhere. Not a lot of meaning in that. You lose a lot of enrichment. You lose a lot of value in that data. This is another way of phrasing that for geology, which you have multiple things. Imagine if you had that. I mean, you wouldn't, what would you do with that? Not very much, right? And so it's the same thing here. Here's an example. I really like this one. This baumhauerite, realgar, and dolomite from a particular Legenbach quarry in Belay, Switzerland. There are, in minerals, have type localities, because things, when you extract something, it doesn't really move. And so there are type specimens, but all minerals have type localities. This particular location is the type locality of 42 minerals. This one is a really nice one. This illustrates two things. First thing is, the big thing in there is dolomite. The red is realgar. The baumhauerite is one of the smallest things in there. It's the silvery gold things on the right-hand side. It's the smallest part of it. So when you talk about how you name the specimen, well, picking primary and secondary is highly subjective. Picking what's dominant doesn't really make sense. Here, it's the smallest thing, and it's a type specimen for that smallest thing. And so it's very hard to do, because if you look at it, like, well, what is that? You have to really look at it. And in fact, on the label, they're all treated as they should be, which are 3 equal parts. It has 3 things in it. Now, you have what it's cataloged under. And because the baumhauerite is the most important thing, it's the type specimen for that, it's then cataloged and organized under baumhauerite. But the specimen itself in the database is split into 3 parts. This is really important because it has to be cataloged under something, right? And in fact, EMU supports this cataloged under notion. So let's talk about opportunities and advantages. So opportunities and advantages. Well, opportunities is an accurate representation of specimens consisting of multiple material entities. It eliminates those generalizations, right? You don't have to say this record is, this radiometric dating record is to this whole specimen. That's a way overgeneralization. You conduct it to the actual part. And therefore it allows you this specimen to actually occur. Without it, the extended specimen network as an overgeneralization doesn't really work at all for geology. And it's really important this happens. And it facilitates interoperability. if you have individual minerals that are kept separate, you have classification codes that you can then, put things together in an interoperable way for geology collections when you treat them separately. Now, great news, Darwin Core DP is currently in public review, and I highly encourage everyone to go check it out. It supports the compound model very quickly. Here, it's a recursive relationship, meaning to self-join in the table, where is part of material entity ID is a join on material entity. So the table in the bottom, quickly, that if you think back to that almandine schist, the first record is the compound specimen, almandine schist, material entity 1. The second record is that garnet, and you can see the 1 is populated in the is part of material entity ID column, and that's a self-join to the 1 in the first row for the compound specimen. Same thing for the bottom one. You have material, rock, schist, it's classified as a garnet mica schist, and that's connected also to the material entity ID. So it's a self-join. So it does. Darwin Core Archive does not support compound model, but Darwin Core DP does. Finally, there are a couple examples. This presentation will be in the notes, will be in the symposium notes with these things. Thank you to the National Museum of Natural History and Smithsonian, the University of Arizona Mineral Museum, and the Peabody Museum, and the Natural History Museum of Bern for providing specimens, and the Natural History Museum of Los Angeles County. Thank you for putting their photos online. It's always valuable information to publish things online, and we really appreciate it because I do go through these things and do use them quite a bit in all kinds of various activities. So I do appreciate it. So thank you all for attending, and I'll take some questions.
Okay, we now arrived at the end of the session. Again, if you have any questions, please put them in the Google Doc and then we will try to answer them. I would like to end the meeting with thanking all the speakers and also thanking everybody involved in organizing this session, including the people involved in getting last minute the missed presentations. Thank you for listening.